Let's modulate that video signal. We were talking about the modem aspect of our signal. How do you put digital data onto a wireless carrier in a way that it is easily and reliably removed at the receiver and interpreted correctly? Now, it turns out that there are going to be, at least for the modem aspect of a wireless link, there needs to be 3 components that we specify. We'll talk about a lot of complicated modulation schemes, but it turns out that there are really only 3 pieces of information that you need to characterize those schemes. How many bits per second are being sent, or what is the symbol rate in our instance? What is the pulse shape? So the strategy for representing digital data is I have a pulse that I'm transmitting, a repetition of pulses, and I'm going to use discrete levels and phases of those pulses on the carrier to represent my data. The pulse shape that I pick and the bit rate together, or the symbol rate together, are going to determine how well my signal fits within a certain bandwidth. Very important, because just like in terrestrial communications, satellite communications are governed by both the FCC and international treaties, and if you are allotted a certain band, you had better stay in that band, or else you make people, your spectral neighbors, very angry. So those 2 pieces of information are necessary, the symbol rate, the symbol shape, the pulse shape, and the signal constellation that we use to map bit states to actual symbol states. And that'll all be a little bit clearer by the end of this talk. So to start off with, you'll hear the term in digital communications, keying. And this is basically, keying is how you represent digital information onto discrete signals. I have a couple examples of the simplest kinds of keying. The first one on the left, where I'm transmitting 1s with a pulse and 0 with nothing. That's called on-off keying. It's the simplest possible keying you can think of. And in this case, my 1s are squares, and my 0s are nothing. We would also call that a unipolar signal. Unipolar because it has DC content. And basically, 0, if I think of 0 as my baseline, I'm throwing a 1 off in a particular direction in voltage, and I'm imparting a DC value to it. If I want a bipolar signal, you can see on the right, I've got 1, 0, 1, 0. I'm using positive rectangles, positive pulses to key with my 1s, and negative pulses to send 0s. Okay. Now, why do I put this on the board? This is all just Digital Communications 101, which hopefully you have seen in some form or another. But I'm going to use it to make a point. Here we've got 2 Fourier transform pairs. We said in the time domain, a Sinc-Function is a box function. And a box is a Sinc-Function. If you understand those 2 Fourier transform pairs, if I start with a box in the time domain, I get a sinc in the frequency domain. If I start with a sinc pulse in the time domain, I get a box in the frequency domain when I take the Fourier transform. If you understand that, you understand all the stuff you need to illustrate the concept of keying and modulation onto an RF carrier that we're going to talk about. Now, here's an important thing to take away. It's one of the cornerstones of analyzing information signals. The way that you learn systems and controls. So I've got a linear system. Let's call it my wireless channel. Or if I'm characterizing a filter in my radio that this signal is passing through. I have an input, I have an output. I take the Fourier transform of the input. I take the Fourier transform of my impulse response of my channel or my filter or whatever thing I'm passing my signal through. If I want to get the output, I multiply those two together and inverse the Fourier transform. Or if I want to work in the time domain, I'm a real masochist. I convolve signals. I convolve X with my channel impulse response. That gives me my output. That works great for deterministic signals. But let's say I'm transmitting a packet with 1,000 bits in it. Those 1,000 bits could be whatever that we want them to be, right? You have to be prepared to transmit every possible combination. Well, in order to figure out how my system operates, will I have to simulate and analyze every potential combination of bits for that packet? That would be 2 to the 1,000 combinations. I think that's more combinations than there are atoms in the known universe, it turns out. So obviously, I'm not going to be simulating that anytime soon. Well, it turns out we can apply some random process theory here to greatly simplify how my signal how to track signal behavior in these otherwise random signals. I don't need to know or simulate every possible waveform that's going through my communication system. Instead, I can characterize it with something called a power spectral density, something that has units of watts per hertz that tells me where is the average spectral energy distributed in this information signal. And that's useful because then I can say, well, here's where the signal energy is for this random signal. And I can build filters that tell me how much energy I'm going to lose when I pass that signal through it. Now, if I have a frequency selective channel, I can see how much of that signal is actually going to make it through my radio channel that's frequency selective. And it gives me a nice statistical tool for analyzing the general case of these information signals. Okay. Now, here's one of the most important theorems. And you probably invoke it all the time if you do work in digital communications. You don't even realize that you're doing it. It's so important and foundational. Here's the basic concept. If I have a pulse, in the previous slide it was square pulses. Fourier transform would be a sinc, right, in the frequency domain. If I have a pulse, and I make a bunch of random ones and zeros with those pulses, and in general, those ones and zeros are uncorrelated with one another. Like, in other words, they're a really good information sequence. I have the same number of ones and zeros. If I had a whole bunch of ones and not nearly as many zeros, then obviously I didn't do compression very well, right? So any compressed signal will fit this criterion very nicely. And if there's no correlation of ones and zeros, there's no real pattern. I've removed the pattern with decompression, with compression techniques. If it's a rich data stream, and I'm modulating pulses in the time domain of P of t, then my power spectral density will be proportional to P of f magnitude squared. Remember, power spectral densities are always real valued, and they represent the power per hertz in a signal. What this says is if I take a pulse and I make a rich data stream from it by modulating ones and zeros onto that pulse, my power spectral density will eventually look like the magnitude of that pulse's Fourier transform squared. If I do a bunch of rectangles, my power spectral density will eventually take the shape of sinc squared. Be a nice big peak and then little ripples that die out as I move away from that peak. And that's a really important theorem because now we know kind of what the signal is doing, even though we haven't pinned down exactly what that signal is. We just know it was generated with rich data modulated onto pulses. But that goes to show you also that there's an interesting degree of freedom in designing a communication system. And that is, different pulses will result in different signal spectra. So for example, if I take these square wave, I'm just showing a 1, 0, 1, 0. But if I have a very long data that has a rich collection of ones and zeros, I will eventually get a squared sinc power spectral density. And that last term on there, that little delta term, you can normally ignore that. That only exists in case you have a unipolar type modulation scheme. For example, in this example where I've got a pulse and then basically a zero amplitude box to represent my 0 bit. The net effect is that I have a DC component. So it makes sense that there's going to be a spectral line at f equals to 0 represented by that delta function riding along with my sinc squared signal. So, if I wanted to, I could pick another signal. I could pick triangles instead of squares. One of the things, squares, it turns out, are lousy pulses for sending information. They're really easy to generate. You just put out a voltage of 1 or 0 or 1 or negative 1 to represent it. Very easy to generate electronically. Lousy from a spectrum point of view because the sinc function, its little spectral side lobes, take a very long time to die out. It rings quite a bit. And so you will leak a lot of energy out of band if you use square pulses in radios. That's why almost nobody uses square pulses when you modulate data. But the principle is there. If I wanted to smooth things over, I could use triangles. Triangle of a certain amplitude and a negative triangle or a 0 triangle for my zeros, positive triangle for my ones. And of course, what's the Fourier transform of a triangle? Fourier transform of a triangle is a sinc squared, which means it's actually be sinc to the 4th will ultimately tell me where the spectral energy in my power spectral densities is distributed. Sinc to the 4th dies out a lot faster than sinc squared. So triangles would clearly be a better way, if I could generate them, than a pulse. Okay. Well, that kind of makes sense, right? If my pulses are smoother, then they should have less high-frequency components. So then when I modulate them and put them on an RF carrier, they should have less stuff leaking into adjacent bands. The only problem is, the way I've presented it here, I am only using pulses that are going to fit within a certain symbol period. So you can see here I have 4 symbol periods sketched out, and all of my pulses, my square wave, fits nicely in that symbol period. And I can try to smooth things over, make triangles or maybe little bell curves or things that reduce the frequency content and keep me from rippling. But one of the problems is I'm going to go to 0 at either end of that symbol period, and I'm going to stay at 0, which means the support of my pulse, there's that word again that we learned in antenna engineering, the support of my pulse is only 1 symbol period, nothing more. That automatically means I'm going to have some high-frequency energy. Why? Because we know that the support theorem, when we studied in antennas, said that if I start with a finite support pulse in the time domain, that means my frequency domain has to have infinite support. And in fact, the more support, the less support I provide in the time domain, the more high-frequency components I'm going to have to. You can show that pretty easily as well. So wouldn't it be nice if I had a pulse that I could put digital information on? I could key it with positive or negative values that was bigger than a symbol period. Does that seem like a contradiction? Well, in most cases it would be, right? If I had a pulse that was bigger than the symbol period, then my pulse would bleed into the neighboring pulse slots, and I would destroy the ability to detect the amplitudes of my pulses. Unless I do something very, very clever. The clever thing comes on the next slide. What if I used sinc pulses, for example, in the time domain? Well, the sinc pulses would overlap. However, remember that the sinc function periodically crosses 0 value at uniform regular intervals. If I put my next sinc pulse such that its peak amplitude that I try to estimate lines up with the next 0, then those pulses are going to bleed together. But at that particular value, as long as I space all of my sinc pulses at an even interval, at that particular value, all the other sinc pulses will be crossing 0, and the only non-zero value that will be contributing to that location is the amplitude of the pulse that I want to read the bit out of. Does that make sense? Right? I'm lining up my sinc pulses, like I'm showing 2 adjacent sinc pulses here. You'll see that when one is 0, the other one is at a maximum. And when the other one goes to 0, the other one is at a maximum. So at those 2 points, as long as I'm synchronized very carefully and I read the amplitude of my signal, it represents the amplitude only of that sinc pulse. So now I've reduced digital detection. The only caveat here is now I have to use a special device to do my detection. Not one that tries to reproduce the fidelity of the digital signal. I don't need to do that because I don't really care what's going on in between those 2 digital pulse amplitudes that I'm trying to read. All I want to do is estimate the amplitude of that sinc pulse at precisely that location. And this location. I don't care about any of the stuff in between. So I need a special creature, a special device that does exactly that. And if so, I can use pulses that exceed my symbol period. In fact, there's an infinite number of pulses that satisfy this criterion. This is called the Nyquist intersymbol interference criterion for overlapped pulses. You use any pulse shape that you want as long as it goes to 0 at regular intervals where you plan to read the other digital pulse amplitudes. So, what does that mean? Well, think about it. If I can send data on sinc pulses, what's the Fourier transform of the sinc pulse? It's a box. Ideally, all of my spectrum would fit exactly in finite limits and nothing else outside. This is a wonderful way to control RF spectrum. Now, there's a fundamental problem. We know that to make a true box in the frequency domain, you need an infinite support pulse. We don't have that kind of time. We're finite creatures, mortal. We can't be generating infinite support time domain pulses to send digital data. And so we're going to have to make some realistic compromises, right? So let's do a little experiment. I have a couple sketches here just to illustrate the trade-offs in pulse shaping. We have a sinc pulse there. I just made that in MATLAB. And I've got basically 40 instances where it crosses 0. It crosses 0 40 times in that diagram, basically at 40 unique points, except for the very center point where it peaks. And that's what I'm going to code my amplitude onto and represent digital data with discrete amplitude levels of that pulse. Now, I took the Fourier transform, and sure enough, I see a box. I actually see a little bit of rippling at the corners of the square wave, and you can see that it doesn't quite go to 0. In fact, you could see quite a bit of spectral energy if I put this in the logarithmic domain, but I don't think I did for this particular plot. You see just a little bit of curving off. And that's an artifact of the fact that I don't have an entire sinc pulse. I only have plus or minus 20 cycles of a sinc pulse. I had to truncate it at some point to get it to fit into MATLAB. And so a realistic truncation like this produces a little bit of ringing, and then, again, infinite support outside of the box. But it looks kind of like a box, so at least we know the behavior is appropriate. Okay, so there's 2 problems we're dealing with now. I need infinite support, which is not reasonable. The other thing is, let's say time is equal to 0. That's when I want to generate a pulse. I get a bit, and if I want to send that particular pulse, I now have to go back in time, -20 units, start ramping up, At time equals 0, I make a pulse, and then I start wiggling down. So if I want to send this pulse at time equals to 0 when a bit comes in, I've got a bit of a problem with causality. Okay, that's not a problem, right? I can just allow some latency. Digital communications operate at speeds where you will never notice the latency even in a real-time system. We're talking microseconds here. I will simply, first I have to truncate this for time less than 0, and then I have to shift it. Well, let's first do the truncation to show where that works, what that does. Whenever I truncate something, I really mess it up in the frequency domain. I truncated my sync pulse so that it still satisfies the Nyquist intersymbol interference criterion. It is also now causal, but look what I did in the frequency domain. I sprayed energy everywhere. I did convert this over into the logarithmic scale, but look at that. I'm still only 20 dB. Let's see, I've got a peak at negative 5 dB, and I'm still only about 20 dB down at negative 4, which is basically 4 times outside the bandwidth. So if I took the center frequency of this pulse, I put it on an RF carrier, and I moved to the edge of my band, 4 times that distance, I'm still only 20 dB down in signal energy. This is a terrible way to send information. But okay, let's tolerate some latency. Let's take that sync pulse and shift it over. Oh, that's nice. There we go. Shifted and truncated. Here I've only got 4 symbol periods of support for my sync pulse. So this might be a little bit more realistic in terms of what I could generate with a chip. I have to basically send in a digital sequence. And you can buy chips now that basically you put in the digital sequence and it'll output a sync or a related type of pulse over a certain interval. So this one you could say, I'm going to set the interval to 4 symbol periods. I'm satisfying my Nyquist intersymbol interference criterion, and it'll put out a nice pulse chunk. I can put my digital information on that. In the frequency domain, I'm doing a lot better spectrally than when I just truncated it at 0 without shifting it. You can see I've got a nice peak in my signal spectrum. My first lobe is below negative 20 dB in terms of the peak, and you see it nicely falls off after that. Still may not be good enough for whatever criterion that your regulatory agency has specified. I put this on a carrier, and they say, well, you've got to be at least 50 dB down from your peak signal strength when I get more than 100 megahertz outside of your band. And you look and you do your Fourier transform and you say, uh-oh, I'm violating that criterion. Well, what are your options at this point? You have 2 options. You can either slow down your transmission. What does slowing down the transmission mean? That means I've got to take my pulse and I just stretch it out in time. I transmit fewer symbols per second, fewer bits per second. And that will, in the frequency domain, squish the spectrum. So now some of those large peaks are going to be brought within your allotted bandwidth, and you'll meet the regulatory agency's criterion. The other option that you have is to change the pulse shape. Maybe I need to expand the cycles of the sync. What would that do? Well, now here's a causal sync with about 8 cycles in there thrown in. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So about actually 10, a support of 10 symbol periods. And look how nicely that rolls off in the dB scale. You see, adding a few extra lobes goes a long way for collapsing your signal strength into a finite band. Do you have any questions? Yeah.
You still need more time to generate that pulse. So.
That's right. That's right. That's right. It's a trade-off, right? Here, now I have to have hardware that can support the generation of a longer pulse. I need to start ramping up ahead of time. Now I'm introducing, in this case, about 5 cycles of latency. But again, because these things are usually sub-microsecond symbol intervals, transmitting millions of pulses per second, you'll never notice in terms of a user that latency. There are other sources of latency that you have to worry about much more than this. But your hardware has to have the complexity to kind of ramp up, like you're saying, to do that. Was that the point that you made?
No, I was more thinking, so what would be the difference? Because now you said we have two choices, either like adding a ripple or in the temporal domain, or widening the peak.
That's right. That's right.
So for frequency.
Well, yeah, those are two ways to collapse your signal spectrum. That's right. That's right. Now, why would you choose one versus the other, right? So if I understand your question correctly, why not just use this as the bit and not this as the symbol, but transmit at the same rate? Was that your point? So you're saying, well, you're occupying more time, just like you would if you slowed down. Yeah. The only difference is by using let's say that you normalized this pulse so it was the same length as this pulse, right, in time. That means that if you stretch this one out, this would actually compress the frequency domain spectrum. Would it compress it as well as this does? Maybe or maybe not. Depends on what regime you were looking at in your frequency domain. However, this pulse only satisfies the Nyquist intersymbol interference criterion if you're transmitting at a rate that's now dilated compared to this pulse. In other words, they may do similar jobs of collapsing frequency inside your band, frequency content inside your band, but I can put my next symbol a lot closer to the peak in this one. So I can maintain a high data rate. So this is a sneaky way to sort of have your cake and eat it too. Collapse your signal spectrum, but not compromise your data rate. So it's a very insightful question to ask. Now, it turns out there's a whole family of these types of pulses. Here's a common set of pulses used. They're called raised cosine pulses. That SN, there's a mathematical formulation. You see there's a SN, that's the Sinc-Function. So they're related to the Sinc-Function. They all kind of look like Sinc-Functions. They're pulses that periodically cross zero. But then there's all these extra terms. There's this cosine term, and there's this 1 over 4 kappa F naught T squared. F naught is the fundamental frequency of your zero crossings. Kappa is the roll-off factor. It's a value between 0 and 1. If kappa is equal to 0, it's a Sinc-Function. The cosine term and the denominator go away, and you're just left with the sinc. When you add kappa, now your cosine pulse rolls off a little faster in the time domain. And what that means in the frequency domain, somebody must have stayed up all night working this Fourier transform out with their tables. They found that the Fourier transform is like a box that rolls off with a cosine component. So it makes the transition, instead of going abruptly down to 0 in the frequency domain, depending on the value of kappa, it rolls off with a cosine characteristic in this transition region that I've outlined up on the board. So basically, when kappa is equal to 0, I get a box. Sinc-Function in the time domain, box in the frequency domain. When I set kappa equal to, say, 0.5, I get a flat region that then transitions smoothly to 0 outside that region. When I set kappa equal to the maximum value of 1, what happens, I don't even have a flat region anymore. My spectrum looks like just a cosine hump. Starts at 0 outside the band, transitions higher, and then lower. And so people love these raised cosine pulses, or sometimes they call them root-raised cosine pulses because they use the square root of this spectrum to generate the pulse in the time domain. you get this family of pulses that's just like the sinc function, crosses zero at even intervals. Therefore, it satisfies the Nyquist intersymbol interference criterion. And it turns out that kappa is really nice for adjusting the roll-off of your signal. By ramping up kappa, you get functions in the time domain that are more amenable to clipping. You can clip their support in the time domain, and they ring less in the frequency domain. The trade-off is that you got to at least include a little more margin of error to account for these cosine transitions. So your signal might take up a little bit more bandwidth immediately around the center frequency, but those little lobes, spectral lobes that you see ringing off, will dampen more. And so this is a nice tool that the communications engineer uses to design their pulses. So this whole field of communications engineering is called pulse shaping. So if you ever see that, a section of that in a communications book, they're just basically saying tweaking pulses in the time domain so that they satisfy Nyquist ISI and they fit within my spectral constraints when I modulate it up to a carrier. There's a really nice exercise that you can do online. I believe there's a sample homework problem. I'm not going to have you do this, but there's this example of an answer online as well. So if you want to go ahead and do it. It's an illustrative exercise to try to design a pulse to fit a certain bandwidth. And so I have, as part of the homework exercise online, you can go and there's a spec written very similar to how the FCC would require a wireless spec to be written, saying, hey, I think it's using the ISM band. Here's the ISM band. Make a pulse that fits within the 80 or 100 megahertz of spectrum, about 2.4 gigahertz, and is 50 dB down from your peak value outside that spectrum. Find the pulse that I can compress in the time domain the most. It has to have 4 cycles of support. But otherwise, as long as you can do that, you can compress it the most in the time domain. And what is the ultimate symbol rate and hence bit rate that will encode information and modulate information and still fit within that spectral mask of constraints. So it's a good exercise to work through. Now, it turns out that we are almost at the end of the class period. Look at that. Let me finish with asking you a question. We now have this digital sequence where the bits have been keyed up on pulses that occur at regular intervals. All those pulses are going to blend together, except at these very discrete points where I want to estimate the amplitude of that pulse. I now need to run this signal through hardware or some sort of equivalent signal processing in software, a device that pulls out the best, cleanest estimate of that pulse amplitude. What is that device called? It turns out that there is an optimal device that is the best possible detector, amplitude estimator at that particular point. And then I feed that into decision algorithms and other processing software. I do my channel decoding. I do my decompression. I do all my other stuff after that. But I need to condition my input signal in such a way that produces really nice estimates of my pulse amplitudes. Otherwise, I can't make a decision of what kind of bit or bits were modulated onto that pulse. What is that device called? Starts with M. M-A. M-A-T. I know you really. This is the shyest class I've ever had. You're all awake. Very few of you have dozed off. This is good. It's the matched filter, right? Did you learn that in your communications classes? That turns out to be the optimal linear detector because it's not like a regular filter where you're trying to get the highest signal fidelity. You're actually not doing a really good job of reconstructing your original signal in a matched filter. But you can show that the matched filter, which is where we'll start our discussion on Tuesday, the matched filter at the output produces the highest possible SNR estimate of the amplitude at that particular point. Anything before and after can go to hell for all we care, because you don't need that to detect a bit.